Thank you for listening to the Sleepy Mind channel. The vanilla orchid is the only orchid that produces an edible fruit, and it grows not as a tree or a bush, but as a long climbing vine that relies on surrounding structures for support. Its growth is slow, deliberate, and shaped by warm air, filtered light, and the steady movement of moisture through a tropical forest environment. Understanding vanilla begins with how the plant lives before it ever produces a flower or a pod. And if you like stories like these, please like and subscribe. Vanilla comes from the species Vanilla planifolia, a member of the orchid family adapted to life in humid forests. Unlike plants rooted deeply in soil, vanilla orchids grow as epiphytes. This means they climb trees or other supports, rather than drawing nutrients from the ground. The vine attaches itself using aerial roots that cling to bark and rough surfaces, anchoring the plant as it grows upward. Let's begin. In its native habitat, the vanilla orchid grows in tropical regions of Central America, where temperatures remain warm and humidity stays high throughout the year. These forests provide dappled light rather than direct sun. The orchid's leaves are broad and flat, designed to capture filtered light while avoiding damage from intense exposure. Too much sun scorches the leaves. Too little light slows growth and delays flowering. The vanilla vine grows steadily, adding length rather than height. When supported, it can extend more than 30 feet along tree trunks or trellises. This length allows the plant to spread its leaves across a wide area, increasing photosynthetic capacity without investing in thick stems. The vine remains flexible, bending and wrapping as it climbs. Vanilla orchids do not grow in soil like typical plants. Their aerial roots absorb moisture and nutrients from the air, rain, and debris that collects on bark. Organic material trapped along the vine provides small amounts of nourishment. This method of feeding makes the plant sensitive to dry air and poor humidity. When the surrounding air becomes too dry, growth slows or stops. Because the orchid relies on air and surface moisture, consistent humidity is critical. Sudden drops in humidity cause stress, leaves lose firmness, roots dry, and energy transport through the vine becomes less efficient. In consistent conditions, moisture moves steadily through the plant, supporting slow but continuous growth. Vanilla orchids grow slowly compared to many crops. It often takes 3 to 4 years before a vine reaches maturity and produces flowers. During this time, the plant invests energy into extending the vine, strengthening attachment points, and building leaf area. Flowering does not begin until the vine has accumulated sufficient length and stored energy. The flowers of the vanilla orchid are large and delicate, with pale green to yellowish petals. Each flower opens only once and remains receptive for a single day. If pollination does not occur during that brief window, the flower falls off and does not return. This short bloom period shapes every aspect of vanilla production. In the wild, vanilla orchids are pollinated by specific native bees found only in their original habitat. These bees have the size and behavior required to navigate the flower's structure. A thin membrane separates the male and female parts of the flower, preventing self-pollination. The pollinator must lift this membrane and transfer pollen precisely for fertilization to occur. Outside native regions, these bees are absent. As a result, nearly all commercial vanilla relies on hand pollination. Each flower must be pollinated individually, by hand, on the single day it opens. The process requires careful timing and steady technique. A thin stick or tool is used to lift the membrane and bring the pollen into contact with the receptive surface. Successful pollination produces a long green pod that grows slowly from the flower. This pod is often called a vanilla bean, but botanically it is a capsule. After pollination, the pod develops over 8 to 9 months. During this time, the vine must remain healthy and stable. Stress from drought, temperature swings, or poor care can cause pods to abort before maturity. Fresh vanilla pods have little aroma. The familiar vanilla scent does not exist at harvest. Instead, flavor develops through a long curing process that begins only after the pod is picked. This means the plant's role extends far beyond flowering. It must sustain months of pod development before flavor can even begin to form. The curing process begins with heating or blanching the pods. This stops growth and activates enzymes inside the pod. The pods are then wrapped and allowed to sweat. Sweating encourages chemical reactions that produce aroma compounds. Over several weeks, pods darken and shrink as moisture is released and flavor develops. Proper curing takes months. During this time, vanillin forms as the primary flavor compound, alongside more than 200 additional aroma compounds that contribute to vanilla's complexity. This chemical richness is difficult to reproduce artificially. This is why natural vanilla remains distinct. Vanilla orchids are sensitive to environmental stress throughout this entire process. Too much sun damages leaves, too little light reduces flowering, poor airflow increases fungal risk, sudden environmental changes reduce productivity. Because the vine grows slowly and stores energy in its length, stability matters more than speed. Older vines often produce better pods. Over time, the plant develops more efficient internal movement pathways and greater stored energy. Vanilla orchids benefit from long-term consistency rather than rapid expansion. The plant cannot be rushed into production. Each harvest reflects years of preparation. Vanilla farming is labor-intensive. Each pod represents months of care, from vine training and pruning to daily monitoring during flowering. Most vanilla is grown by small-scale farmers who rely on careful attention rather than mechanization. Weather disruptions, such as cyclones, can destroy entire crops, making production unpredictable. These challenges contribute to fluctuating vanilla prices. Supply relies on successful flowering, pollination, pod development, and curing. Any interruption along this chain affects availability. Synthetic vanillin exists, but it lacks the complexity of natural vanilla. This remains reserved for premium uses. Vanilla orchids reward patience. Their growth reflects long seasonal cycles rather than quick returns. The plant's needs shape the rhythm of farming life, linking forest ecology with human craftsmanship. Every vanilla bean traces back to a single flower that opened for one day and was pollinated by hand. Understanding the vanilla orchid begins with recognizing this slow, deliberate process. Before flavor, before fragrance, and before harvest, the plant spends years growing quietly, storing energy, and waiting for conditions to align. This foundation shapes everything that follows. Vanilla orchids depend on careful structure and steady support to grow over many years. Unlike plants that stand upright on their own, the vanilla vine relies on surrounding surfaces to guide its movement and shape its development. How the vine is supported, trained, and pruned determines how efficiently it produces leaves, flowers, and eventually pods. In natural forests, vanilla orchids climb tree trunks and branches. The vine grows upward and outward, attaching itself with aerial roots that press against bark and rough surfaces. These roots do not draw nutrients from the tree. Instead, they act as anchors, holding the vine in place while allowing leaves to spread into filtered light. This climbing habit influences how energy moves through the plant. As the vine extends, sugars produced in the leaves must travel along its length to support new growth, flowering, and pod development. A well-supported vine allows energy to move efficiently without excessive bending or damage. Unsupported or poorly trained vines often twist, kink, or break, interrupting transport and slowing growth. In cultivation, growers replace trees with trellises or support posts. These structures guide the vine into manageable patterns. The goal is not height alone, but accessibility. Flowers must be within reach for hand pollination, and pods must be easy to monitor and harvest. For this reason, vines are often trained horizontally after reaching a certain height. Training the vine changes how growth is distributed. When the vine is allowed to grow straight upward, it prioritizes extension rather than flowering. Once redirected horizontally or gently looped downward, the plant shifts energy toward reproduction. This change occurs because gravity and growth hormones alter how energy is allocated along the vine. Pruning plays a central role in this process. Vanilla orchids grow continuously unless directed otherwise. If left unpruned, the vine may become excessively long, with energy spread thinly across many leaves. Strategic pruning shortens transport distance and concentrates energy where flowers are more likely to form. Pruning also improves airflow around the vine. Dense growth traps moisture, increasing fungal risk. Removing excess length and older sections allows air to circulate more freely, helping leaves dry after rain or irrigation. This reduces disease pressure without chemical intervention. The vine stores energy within its length. Each section acts as a reservoir that supports future flowering and pod development. Older sections often store energy more efficiently than younger growth. For this reason, mature vines tend to produce better pods than newly established ones. However, excessive age can also reduce efficiency. Over time, older sections may accumulate damage or disease. Balancing new growth with retained mature sections allows the plant to benefit from stored energy without sacrificing health. Spacing between vines matters as well. Vanilla orchids require good air circulation to remain healthy. When vines are grown too close together, humidity increases and airflow decreases. This creates conditions favorable to fungal infections. Adequate spacing reduces this risk and supports gradual growth. Light exposure must be carefully managed. Vanilla orchids require shade and filtered light rather than full sun. Leaves exposed to intense sunlight scorch easily, reducing photosynthetic capacity. Leaves grown in too much shade produce insufficient energy, slowing growth and delaying flowering. Growers often use shade cloth or natural canopy cover to regulate light. The goal is even indirect illumination throughout the day. This stable light environment supports consistent leaf function and reduces stress that would otherwise delay flowering. Temperature stability also affects vine development. Vanilla orchids prefer temperatures between 70 and 85 degrees Fahrenheit. Within this range, metabolic processes proceed steadily. Cold temperatures damage vines, slowing growth and increasing susceptibility to disease. Sudden temperature changes disrupt energy transport along the vine. Humidity remains essential throughout this stage because vanilla orchids absorb moisture from the air and surface debris. Dry conditions reduce water availability even when roots appear healthy. Consistent humidity supports leaf firmness, root attachment, and nutrient absorption. Air circulation must balance humidity. Stagnant air encourages fungal growth, while excessive airflow dries leaves and roots. Proper spacing, pruning, and environmental control maintain this balance, allowing moisture without stagnation. The structure of the vine determines when flowering begins. Flowering usually occurs only after the vine reaches sufficient length and maturity. This ensures that enough stored energy exists to support pod development over many months. Stress during this stage delays flowering. Improper pruning, poor support, or inconsistent conditions divert energy towards survival rather than reproduction. Because flowering occurs only once per year in most cases, missed opportunities delay harvest significantly. Once flowers appear, the vine must remain stable. Movement, breakage, or stress during flowering reduces pollination success. Well-trained vines hold flowers in accessible, protected positions, supporting careful hand pollination. After pollination, structural stability becomes even more important. Developing pods hang from the vine for many months. Weak supports allow bending and damage, increasing the risk of pod loss. Strong, evenly distributed supports prevent strain on attachment points. Throughout this period, growers monitor vine condition closely. Leaf color, firmness, and growth rate indicate whether energy movement remains balanced. Yellowing leaves suggest nutrient imbalance or stress. Soft or wrinkled leaves indicate moisture problems. Adjustments during this stage focus on preserving stability rather than increasing growth. The vine has already committed energy to reproduction. Supporting that commitment requires steady conditions rather than intervention. The relationship between vine structure and productivity defines vanilla cultivation. Unlike crops that can be replanted quickly, vanilla requires long-term planning. Decisions made years earlier determine how the vine behaves during flowering and pod development. Understanding this structural dependency explains why vanilla orchids are slow to produce but capable of sustaining productivity over many years. The vine's length, training, and support create a framework that either supports or limits future harvests. Every pod produced reflects not only successful pollination, but years of careful vine management. The plant structure carries the history of those decisions forward, shaping outcomes long after pruning and training have occurred. In this way, vanilla orchids transform structure into potential. The vine itself becomes both storage and pathway, holding the energy required for flowering while delivering resources where they are needed. When structure and care align, the orchid produces steadily without exhaustion. Vanilla orchids depend on precise environmental balance to maintain gradual growth. Their vines, leaves, and aerial roots function within narrow ranges of humidity, temperature, airflow, and light. When these conditions remain stable, growth continues quietly. When they drift outside tolerance, the plant responds by slowing or redirecting energy. Humidity is one of the most important factors. Vanilla orchids absorb moisture not only through their roots, but also through the surfaces of aerial roots and surrounding tissues. In humid air, moisture condenses on root surfaces and leaf cuticles, supporting hydration without constant water contact. When humidity drops, this surface moisture disappears, and water movement through the plant slows. Dry air causes leaves to lose firmness. Cells lose turgor pressure as water evaporates faster than it can be replaced. Growth slows, and the vine conserves energy by reducing expansion. Extended dry conditions can halt growth entirely, even if the plant appears otherwise healthy. Humidity must be balanced with airflow. While moisture supports hydration, stagnant air creates conditions for fungal growth. Fungal spores thrive when leaves remain wet and air does not circulate. Vanilla orchids are especially susceptible because their vines form dense networks if not managed. Good airflow allows moisture to evaporate gradually after rain or irrigation. This reduces the time leaves and roots remain wet, lowering disease risk. Air movement also helps regulate temperature around the plant, preventing localized heat buildup that can stress tissues. Temperature stability is equally important. Vanilla orchids prefer temperatures between 70 and 85 degrees Fahrenheit. Within this range, metabolic processes proceed steadily. Enzymes function efficiently, sugars move through the vine at predictable rates, and tissues remain flexible. Cold temperatures disrupt these processes. When temperatures drop, metabolic activity slows, energy transport through the vine becomes less efficient, and growth pauses. Prolonged cold can damage vine tissue, leading to darkened, weakened sections that recover slowly. Sudden temperature swings create additional stress. Rapid cooling followed by warming forces the plant to repeatedly adjust metabolic rates. These adjustments consume energy that would otherwise support growth or flowering. Over time, frequent temperature swings reduce productivity. Light interacts with both humidity and temperature. Vanilla orchids require filtered light rather than direct sun. In forest environments, canopy cover diffuses sunlight, creating even illumination. Leaves are adapted to this light level, with broad surfaces that capture diffuse rays efficiently. Direct sunlight damages vanilla leaves. Intense exposure heats leaf tissue quickly, causing water loss and cellular damage. Scorched areas reduce photosynthetic capacity and become entry points for disease. Too much shade, however, limits energy production, slowing growth and delaying flowering. Maintaining consistent light exposure supports steady leaf function. Growers often adjust shade gradually rather than abruptly. Sudden changes in light intensity force the plant to adapt quickly, diverting energy from growth to repair. Water availability must support humidity without saturating tissues. Vanilla orchids do not grow in soil like most plants, but their aerial roots still require moisture. Watering practices aim to moisten surfaces and surrounding material rather than flood the plant. Excess water creates problems. When moisture lingers on leaves and vines without sufficient airflow, fungal infections develop. Roots may rot if debris accumulates and remains wet. Proper drainage and careful watering prevent these issues. Vanilla orchids absorb nutrients from organic debris that collects around roots and vine joints. Decaying leaves, bark fragments, and dust provide trace nutrients. This slow nutrient supply supports gradual growth without rapid spikes. Over-fertilization disrupts this balance. Excess nutrients push the plant into rapid leaf growth, producing soft tissue that is more vulnerable to disease. Balanced, minimal feeding maintains tissue strength and supports long-term health. Environmental stress affects flowering timing. Vanilla orchids flower only after years of growth under consistent conditions. Stress during vine development delays flowering by diverting energy towards survival. Even short disruptions can postpone blooms by months or years. Because each flower opens for only one day, environmental stability during flowering is critical. Excess heat, dryness, or humidity changes on that day reduce pollination success. Consistency across weeks leading up to flowering improves outcomes. The orchid's sensitivity makes it an indicator of environmental balance. Healthy vines show firm leaves, gradual growth, and regular spacing between nodes. Stressed vines show wrinkled leaves, uneven growth, or darkened sections. Growers monitor these signs closely. Adjustments are made gradually to avoid compounding stress. Increasing humidity slowly, improving airflow incrementally, or adjusting shade across seasons allows the plant to adapt without shock. Long-term stability benefits vanilla orchids more than short-term optimization. Rapid improvements followed by setbacks are less effective than moderate conditions maintained consistently. The plant responds best when change is predictable. This requirement shapes how vanilla is cultivated. Farming systems prioritize shelter, shade, and environmental control over speed. Structures are designed to buffer wind, sunlight, and temperature fluctuations. In regions prone to storms or drought, vanilla cultivation carries risk. Environmental disruptions can halt growth or destroy vines entirely. Because vines take years to mature, recovery is slow. Despite this vulnerability, vanilla orchids thrive when conditions align. Their measured growth reflects a strategy of efficiency rather than speed. By maintaining steady internal processes, the plant sustains productivity over long periods. Understanding these environmental needs clarifies why vanilla cannot be rushed. Each stage of growth relies on the one before it, and stability compounds across seasons. When balance is maintained, the orchid continues growing quietly, preparing for flowering without visible urgency. This environmental sensitivity links the vanilla orchid closely to its surroundings. The plant does not impose itself on the environment. It adjusts in response to it. Growth proceeds when conditions allow and pauses when they do not. As a result, vanilla cultivation becomes a practice of observation and adjustment rather than force. The plant guides the pace, and success relies on respecting that pace rather than accelerating it. Vanilla orchids reach a turning point when they begin preparing to flower. This phase does not arrive suddenly. It follows years of vine growth, gradual energy storage, and repeated exposure to consistent conditions. Flowering is not triggered by a single cue, but by the accumulation of readiness within the vine. The vine itself stores energy along its length. As leaves photosynthesize, sugars move through the vine and are held in tissues that remain active for long periods. Older sections of vine often contain more stored energy than newly grown tips. This is why maturity matters. A vine that has reached sufficient length and stability can support flowering without exhausting itself. Flower buds form at nodes along the vine. These nodes appear where leaves join the stem. Not every node produces a flower. Flower initiation relies on how much energy is available after the plant meets its basic needs for growth and maintenance. When energy supply is limited, nodes remain vegetative and produce only leaves. Pruning influences this balance. When the vine is shortened or redirected, energy that would have supported further extension is redirected toward existing nodes. This redistribution increases the likelihood that flower buds will form. Poorly timed or excessive pruning, however, removes stored energy and delays flowering. The position of the vine also affects flowering. Vines trained horizontally or gently downward tend to flower more readily than those growing straight upward. Gravity alters hormone distribution within the plant, changing how growth signals are expressed along the stem. This shift encourages reproductive development over continued extension. Light exposure at the node level matters as well. Nodes receiving filtered light without overheating are more likely to initiate flowers. Dense shading reduces energy production, while excessive sun damages tissue. Balanced light supports the slow build-up required for flowering readiness. Once buds form, development proceeds gradually. Buds remain small and inconspicuous for weeks. During this time, the plant continues to assess conditions. Stress from drought, temperature swings, or disease can cause buds to abort before opening. This protects the plant from committing to reproduction when survival is uncertain. When conditions remain stable, buds enlarge and differentiate into flowers. The vanilla orchid flower is large relative to the vine, with pale green to yellowish petals. Its structure is complex and delicate, designed to limit pollination to very specific interactions. Each flower opens for only a single day. The timing is precise. The flower opens in the morning and closes by the end of the day. If pollination does not occur during that window, the flower falls off and does not return. This brief opening concentrates reproductive effort into a narrow period. The flower's internal structure enforces this restriction. A thin membrane separates the male and female parts of the flower. This membrane prevents self-pollination and ensures that pollen must be transferred deliberately. In native habitats, specialized bees perform this task. These bees have the size, strength, and behavior required to navigate the flower. They lift the membrane and bring pollen into contact with the receptive surface in a single movement. This interaction evolved alongside the plant, creating a highly specific pollination system. Outside native regions, these bees are absent. As a result, natural pollination rarely occurs. Commercial vanilla production depends almost entirely on hand pollination. Each flower must be pollinated manually on the day it opens. Hand pollination requires close observation. Flowers open gradually across the vine, rather than all at once. Growers must inspect vines daily during the flowering period to identify newly opened flowers. Timing errors of even a few hours can result in missed opportunities. The pollination process itself is simple but precise. A thin stick or similar tool is used to lift the membrane and press pollen onto the receptive surface. Too much force damages the flower. Too little fails to transfer pollen. Experience improves success. but conditions still matter. Environmental stability on the day of pollination is critical. Excess heat dries the flower quickly. High humidity can soften tissues. Sudden rain disrupts handling. Even when pollination is performed correctly, stress can cause the flower to abort. Successful pollination produces a visible change within days. The base of the flower begins to elongate, forming a narrow green pod. This pod is often called a vanilla bean, though botanically it is a capsule. Its formation marks the plant's full commitment to reproduction. Once the pod begins developing, the vine enters a long support phase. The pod grows slowly over 8 to 9 months. During this time, the plant must continue supplying water, sugars, and nutrients without interruption. Stress during this phase can cause pods to stop developing or drop prematurely. Because pods hang from the vine for many months, structural stability becomes essential. Weak supports allow movement that damages attachment points. Strong, evenly distributed supports reduce strain and protect developing pods from breakage. The plant cannot compensate for errors at this stage. Missed pollination means no pod. Aborted pods mean months of lost effort. Each successful pod reflects precise timing, consistent conditions, and careful handling. Flowering in vanilla orchids is therefore rare, brief, and consequential. It represents the point where years of preparation are tested in a single day. This is why flowering is treated as the most critical moment in vanilla cultivation. Understanding this process clarifies why vanilla orchids produce relatively few pods despite long vines. The limitation is not growth, but reproduction. The plant restricts flowering to conditions it can support, protecting long-term survival over short-term yield. The one-day flower window also explains why vanilla farming is labor-intensive. Each flower demands attention at the exact right moment. Missed days cannot be recovered. Success relies on observation rather than automation. Once flowering is complete, the vine's role shifts. It moves from initiating reproduction to sustaining it. The months that follow test the plant's ability to remain stable and healthy while supporting developing pods. This transition marks the beginning of a new phase, where patience replaces urgency. Growth slows, but commitment deepens. The plant has chosen reproduction, and everything that follows relies on maintaining the conditions that made flowering possible. After successful pollination, the vanilla orchid enters a long and demanding phase of development. The brief moment of flowering gives way to months of gradual growth, during which the plant must support a single structure that changes slowly and continuously. This period tests the vine's ability to maintain balance rather than initiate new growth. The fertilized flower begins to elongate at its base. The narrow green structure that forms is the vanilla pod, often called a bean. Botanically, it is a capsule. Its early growth is subtle, with length increasing gradually while thickness remains modest. At this stage, the pod is firm and smooth, with little external change. As the pod develops, water and sugars move into its tissues from the vine. Leaves continue photosynthesis, producing carbohydrates that travel along the stem to support growth. Because the pod develops slowly, this transfer must remain steady over many months. Short interruptions may be tolerated, but repeated stress reduces pod quality or causes development to stop. Pod growth typically takes 8 to 9 months to reach maturity. During this time, the pod increases in length and gradually thickens. Internal tissues form slowly, laying the groundwork for later flavor development. The vine must remain healthy throughout this period because the pod cannot complete development independently. Temperature stability is critical during pod growth. Within the preferred range, metabolic activity supports steady tissue formation. When temperatures drop too low, growth slows and internal development becomes uneven. Excessive heat increases respiration, diverting sugars away from the pod and weakening flavor potential. Humidity continues to matter as well. Consistent humidity prevents excessive water loss from leaves and aerial roots, supporting uninterrupted transport of moisture into the pod. Dry air reduces this flow, while overly wet conditions increase disease risk along the vine and at pod attachment points. Air circulation remains important during this stage. Pods hang from the vine for months, creating shaded, humid pockets. Without airflow, fungal infections can develop on pod surfaces or at joints where moisture accumulates. Proper spacing and pruning reduce these risks by allowing air to move freely. The vine's structure determines how well pods are supported. Each pod adds weight that must be carried by flexible stems. Strong supports prevent bending and twisting that damage attachment points. Repeated movement from wind or handling increases the risk of pod loss, especially as pods grow heavier. During development, the pod remains green and produces very little aroma. Despite its association with fragrance, fresh vanilla pods contain almost none of the scent compounds recognized as vanilla. The chemical precursors exist, but they remain inactive until later processing. This absence of aroma reflects the plant's priorities. During development, energy is directed toward structural growth rather than flavor. The pod functions as a container for compounds that will transform later. Premature aroma production would serve no biological purpose at this stage. Nutrient availability influences pod quality. Balanced nutrition supports uniform tissue development. Excess fertilization, especially nitrogen, pushes the vine toward leaf growth rather than pod support. This imbalance reduces energy allocation to developing pods and weakens future flavor potential. Stress during pod development has lasting effects. Drought, disease, or temperature swings may not immediately kill the pod, but they alter internal structure. Pods that develop under stress often cure unevenly, producing weaker aroma and less complexity. Because of this sensitivity, growers monitor pod development closely. Changes in color, firmness, or growth rate indicate underlying issues. Adjustments focus on restoring stability rather than accelerating growth. As pods approach maturity, their color deepens slightly, and the skin becomes more supple. Length growth slows, signaling that internal development is nearing completion. Harvest timing becomes important. Pods picked too early lack the compounds needed for proper curing. Pods left too long may split or degrade. Harvesting vanilla pods marks the end of the plant's direct role in flavor creation. Once removed from the vine, biological growth stops. However, the most recognizable qualities of vanilla have yet to form. What follows is a transformation driven by enzymes rather than plant metabolism. The curing process begins soon after harvest. Pods are first blanched or heated briefly. This step stops growth and activates enzymes inside the pod. Enzymes begin breaking down complex compounds into simpler aromatic molecules. After heating, pods are wrapped and allowed to sweat. Sweating maintains warmth and moisture, encouraging enzymatic activity. During this stage, pods darken and soften as internal chemistry changes. Aroma compounds begin to form slowly. Sweating occurs repeatedly over several weeks. Each cycle deepens flavor and reduces moisture. The pods shrink as water is released, concentrating aromatic compounds. Careful timing prevents mold, while allowing enzymes to work fully. Following sweating, pods are dried gradually. Slow drying stabilizes flavor and prevents spoilage. Rapid drying halts enzymatic processes prematurely, reducing complexity. This stage can take several months. During curing, vanillin forms as the primary flavor compound. Alongside it, more than 200 additional aroma compounds develop. These compounds interact to create the depth associated with natural vanilla. This complexity is difficult to reproduce synthetically. Proper curing requires attention and patience. temperature, humidity, and timing must be managed carefully. Each batch responds slightly differently based on pod maturity and growing conditions. The curing process reflects both biology and craftsmanship. Once curing is complete, pods are sorted and graded. Quality reflects the entire journey, from vine health and pollination success to pod development and curing technique. Flaws at any stage reduce final value. Older vines often produce pods that cure more successfully. Their internal movement pathway systems are more efficient, and their stored energy supports steadier development. This advantage reinforces the value of long-term vine management. Vanilla pod development illustrates the plant's strategy clearly. Growth is slow, flavor is delayed, and success relies on uninterrupted care. The plant produces few pods, but each one represents months of sustained effort. Understanding this phase clarifies why vanilla is rare and valuable. The plant cannot be rushed. Each pod carries the imprint of environmental stability, vine maturity, and careful human intervention. This long development phase bridges flowering and harvest, transforming a brief reproductive moment into months of gradual change. It sets the stage for vanilla's final form, where patience and process become inseparable from flavor. Vanilla orchids are highly sensitive to disease and physical stress during every stage of growth, but this sensitivity becomes especially important once vines and pods are established. Because the plant grows slowly and commits resources for long periods, interruptions caused by disease or damage have lasting effects that cannot be quickly reversed. Fungal infections present the greatest risk. Vanilla orchids grow in warm, humid environments where fungi thrive. When moisture lingers on leaves, vines, or pods, spores can germinate and spread. Dense growth and poor airflow create ideal conditions for infection, particularly along shaded sections of the vine. Air circulation is the primary defense against fungal disease. Moving air allows surfaces to dry after rain or irrigation. When leaves dry quickly, spores have less opportunity to establish. Pruning excess growth reduces humidity pockets and improves airflow along the vine's length. Spacing between vines also limits disease spread. When vines grow too close together, infections can move easily from plant to plant. Adequate spacing creates physical separation that slows transmission and allows individual vines to be monitored more closely. Moisture management plays a central role. While vanilla orchids require consistent humidity, standing water on plant surfaces increases disease risk. Watering practices aim to raise ambient humidity rather than saturate leaves or vines directly. Excess water trapped in leaf joints or pod attachments becomes a point of infection. Vanilla orchids are also vulnerable to root and stem rot. Although they are epiphytes, debris and organic matter that collect around roots can remain wet if airflow is poor. Rot damages tissues responsible for anchoring and nutrient absorption, weakening the vine's ability to support growth and pod development. Early signs of disease often appear as darkened or softened tissue along the vine. Leaves may yellow or collapse, and pod surfaces may develop discolored patches. Because the vine transports energy along its length, damage in one area affects sections above and below the infection site. Removing infected tissue promptly limits spread. Cutting away damaged sections reduces the load on healthy parts of the vine and prevents fungi from advancing further. Tools must be clean to avoid transferring spores to unaffected areas. Physical damage also creates entry points for disease. Breaks caused by wind, handling, or weak supports expose internal tissue. Because vanilla vines are flexible rather than rigid, repeated movement can weaken attachment points across seasons. Stable supports reduce this risk by limiting strain. Environmental stress increases susceptibility to disease. Heat stress, drought, or nutrient imbalance weaken plant defenses. When leaves lose firmness or growth slows, the plant has fewer resources to repair damaged tissue or resist infection. Consistent conditions strengthen resistance, Vines grown in stable environments with balanced humidity, temperature, and nutrition develop tougher tissues that tolerate minor stress without failure. This resilience reduces the likelihood that small injuries lead to major loss. Vanilla orchids recover slowly from damage. Because growth is gradual, replacing lost tissue takes time. A vine damaged during pod development may not return to productivity until the following season or later. This slow recovery increases the cost of mistakes. The timing of damage matters. Injury during early growth delays vine expansion and flowering. Injury during flowering reduces pollination success. Injury during pod development often results in pod loss. Each stage carries its own risks and consequences. Disease pressure also affects long-term productivity. Repeated infections weaken vines across seasons, reducing flowering frequency and pod quality. Even when infections are controlled, accumulated stress shortens the productive lifespan of the vine. Pruning strategy must balance disease control with energy preservation. Removing too much tissue reduces stored energy and delays recovery. Targeted pruning that removes only damaged or unproductive sections maintains health without exhausting reserves. Hygiene is critical in vanilla cultivation. Fallen leaves, decaying pods, and plant debris harbor pathogens. Regular removal of debris reduces disease pressure and improves airflow around roots and vine joints. Soil and surface cleanliness also matter. Although vanilla orchids do not root in soil, surrounding ground conditions influence humidity and airflow. Wet, cluttered ground increases moisture retention, raising disease risk in the lower vine. Weather events amplify disease challenges. Heavy rains increase moisture levels and spread spores. Storms can damage vines and supports, creating wounds that fungi exploit. Recovery after storms requires careful inspection and repair. Because vanilla orchids take years to reach full productivity, disease prevention is more valuable than treatment. Once productivity is lost, time cannot be recovered. Preventative care preserves future harvests rather than reacting to damage already done. Growers often rely on observation rather than intervention. Subtle changes in leaf color, firmness, or growth rate indicate developing problems. Early correction prevents escalation. The labor-intensive nature of vanilla farming reflects this vulnerability. Each vine must be monitored individually. Small-scale cultivation allows closer attention than large mechanized systems. Disease management links directly to economic stability. Loss of pods or vines affects income for years, not just a single season. This long-term impact shapes how vanilla is cultivated and valued. Despite these risks, vanilla orchids can remain productive for many years when conditions are managed carefully. Healthy vines continue flowering and pod production across multiple seasons without exhaustion. Understanding disease and damage in vanilla orchids reinforces the importance of stability and prevention. The plant does not recover quickly from disruption, but it rewards careful maintenance with sustained productivity. Each pod harvested represents not only successful pollination and curing, but months of protection from stress and disease. The absence of damage is as important as active growth. Vanilla orchids thrive not through resistance, but through balance. When their environment supports slow, uninterrupted development, the plant remains healthy and productive across seasons. Vanilla orchids reveal their long-term behavior most clearly when observed across multiple years. While flowering and pod development draw attention, the plant's ability to continue producing relies on how it manages energy, repair, and preparation between seasons. These longer patterns explain why some vines improve with age while others decline after only a few harvests. Each growing season adds to the vine's internal state. During periods of active growth, leaves produce sugars that support vine extension, flowering, and pod development. When growth slows, some of that energy is retained within the vine rather than used immediately. This stored energy becomes critical for future flowering and recovery. Older sections of vine often store energy more efficiently than new growth. Over time, tissues adapt to repeated transport of sugars and water, forming reliable internal pathways. This efficiency supports stronger flowering and steadier pod development in mature vines compared to young ones. Stress disrupts this process. Drought, temperature instability, disease, or physical damage reduce the amount of energy available for storage. When stress occurs repeatedly, vines enter subsequent seasons with depleted reserves. Flowering becomes less frequent, and pods develop more slowly or abort early. The effects of stress often appear later rather than immediately. A vine may complete one season successfully, yet produce fewer flowers the following year. This delayed response reflects how closely vanilla orchids link current conditions to future performance. Pruning decisions influence this balance across seasons. Removing excess growth concentrates energy into remaining sections of vine. When pruning is done carefully, it shortens transport distances and improves energy availability at flowering nodes. When pruning is excessive or poorly timed, stored energy is lost, delaying recovery. Training methods also affect long-term outcomes. Vines trained gently and consistently develop stable growth patterns. Sudden changes in orientation or support force the plant to reallocate energy toward repair rather than storage. Over time, consistent training supports steadier flowering. Environmental stability plays a central role in multi-year productivity. Vanilla orchids benefit from predictable humidity, temperature, and light patterns. When conditions remain within a limited operating range, the vine adapts to those conditions and refines its internal processes. Sudden environmental changes reduce efficiency. Abrupt shifts in shade, airflow, or moisture force the plant to adjust repeatedly. These adjustments consume energy that would otherwise support flowering and pod development. As vines age, their capacity for sustained production increases if conditions are favorable. Older vines often produce better pods because their internal movement pathway systems are well established and stored energy are greater. However, this advantage relies on avoiding accumulated damage. Disease pressure accumulates across seasons. Even minor infections weaken tissues and interrupt energy flow. Repeated disease episodes reduce flowering frequency and pod quality. Preventative care becomes more important as vines mature. Physical wear also contributes to decline. Years of supporting heavy pods and repeated handling strain attachment points along the vine. Without proper support, older sections become more vulnerable to breakage, reducing productive length. Renewal strategies help manage aging. Allowing new vines to establish alongside older ones creates continuity, while gradually replacing declining sections. These younger vines begin building reserves, while older vines continue producing. Spacing influences long-term health. Adequate spacing allows airflow and light penetration, reducing disease pressure and supporting even growth. Crowded vines experience higher stress and decline faster. Nutrient balance affects aging as well. Consistent, moderate nutrition supports tissue strength and repair. Excess nutrients push rapid growth that weakens structure. Deficiencies limit repair and storage. Water management across seasons shapes vine longevity. Repeated cycles of drought followed by recovery gradually reduce efficiency. Stable moisture allows reserves to rebuild more fully between demanding phases. Seasonal rhythm becomes clearer in established vines. Growth, flowering, pod development, and recovery occur at predictable times. This regularity supports planning and reduces stress caused by uncertainty. The vine's response to dormancy, like slow periods, also matters. Although vanilla orchids do not experience true dormancy, growth slows during cooler or drier periods. These pauses allow energy to accumulate rather than being constantly spent. Recovery during these slow periods supports future flowering. Vines that are allowed to rest under consistent conditions resume growth with greater strength than those pushed continuously. Multi-year productivity relies on respecting these cycles. Continuous pressure for growth or pod production exhausts reserves. Allowing periods of reduced demand preserves long-term potential. The human role in this process is cumulative. Daily care decisions compound over years. Consistent practices create stability. Inconsistent practices introduce stress that reduces longevity. Economic pressure can conflict with biological needs. High prices encourage maximum harvest, but overexploitation reduces future yields. Sustainable cultivation balances immediate output with preservation of vine health. Vanilla orchids demonstrate that productivity is not simply about growth rate. It is about maintaining functional structure across seasons. Vines that grow slowly but steadily often outperform those forced into rapid expansion. Observing vines across multiple seasons reveals subtle changes. Leaf size, color, and spacing shift. Flowering density changes. Pod quality varies. These changes provide feedback about internal balance. Successful growers respond to this feedback. Adjustments are made gradually rather than abruptly. Pruning, training, and environmental management are refined year by year. This long-term perspective explains why vanilla cultivation remains a craft rather than an industrial process. The plant adjusts in response to care at a pace that resists automation. Each productive vine carries the history of years of interaction with its environment. Growth patterns reflect what the plant has experienced and how it has adapted. Over time, vanilla orchids reward patience. Vines that are protected from extremes and allowed to build reserves improve rather than decline. Their productivity becomes more reliable rather than diminishing. Understanding these multi-year patterns prepares the ground for the next phase of the story. Vanilla orchids do not simply grow and fruit in isolation. They exist within wider systems shaped by climate, ecology, and human effort. The behavior of a single vine reflects both biology and environment across time. Each season leaves its mark, shaping what follows. This continuity defines vanilla orchids as plants that turn patience into lasting productivity. Vanilla orchids are deeply shaped by the places where they grow. Climate, forest structure, and regional conditions influence not only how fast vines grow, but how reliably they flower and how well pods develop. These influences are not abstract. They appear directly in vine strength, flowering consistency, and the quality of harvested pods. Vanilla orchids are native to tropical regions of Central America, where warm temperatures, high humidity, and filtered light remain relatively stable throughout the year. In these environments, vines experience few sharp seasonal changes. Instead of distinct growing and resting periods, growth proceeds steadily with minor slowdowns during cooler or drier intervals. When vanilla orchids are grown outside their native range, regional differences become more pronounced. Areas with similar temperature and humidity profiles allow vines to behave predictably. Regions with greater variability introduce stress that alters growth timing and productivity. Temperature patterns play a central role. Vanilla orchids perform best when temperatures remain between 70 and 85 degrees Fahrenheit. Within this range, metabolic processes proceed at a steady pace. Outside this range, growth slows or becomes irregular. Cold temperatures damage vine tissue, while excessive heat increases water loss and respiration. Humidity varies widely between regions and strongly affects vine health. In humid regions, aerial roots absorb moisture easily, supporting continuous hydration. In drier regions, maintaining humidity requires active intervention. Without sufficient humidity, roots dry and lose their ability to absorb water and nutrients from the air. Rainfall patterns also influence regional outcomes. In areas with frequent, gentle rainfall, vines receive steady moisture without prolonged saturation. In regions with heavy downpours, followed by dry periods, moisture availability fluctuates sharply. These fluctuations strain the plant's internal movement pathways systems. Soil and ground conditions influence the microenvironment around vanilla vines, even though the plant does not grow in soil. The presence of organic debris, ground cover, and surrounding vegetation affects humidity and airflow near the vine. Bare ground dries quickly, reducing local humidity. Vegetated ground retains moisture and moderates temperature. Forest canopy structure determines light quality. Dense canopies filter sunlight evenly, creating ideal conditions for vanilla orchids. Open canopies allow direct sun exposure that damages leaves and overheats vines. Too much shade, however, limits energy production and delays flowering. Growers often recreate forest conditions using shade trees or artificial structures. The arrangement of these supports influences light distribution throughout the day. Even, shifting light supports balanced leaf function and reduces stress. Altitude introduces additional variation. Higher elevations often experience cooler temperatures and greater day-to-night differences. These conditions can measure growth, but may support steadier development if temperatures remain within tolerance. However, cooler nights increase the risk of cold damage if temperatures fall too low. Wind exposure differs by region. Gentle airflow reduces disease risk by drying surfaces. Strong winds increase water loss and physically stress vines. In windy regions, additional supports and windbreaks are often needed to protect vines from damage. Regional disease pressure varies as well. Warm, humid areas support fungal growth more readily than drier climates. In these regions, spacing and airflow become critical. In less humid regions, disease pressure may be lower, but water management becomes the primary concern. Vanilla orchids also reflect regional differences in pollination success. In native regions, specialized bees pollinate flowers naturally. In most growing regions, hand pollination replaces this role. The need for hand pollination ties productivity closely to labor availability and skill. Regions with stable weather during flowering periods achieve higher pollination success. Frequent rain, high winds, or extreme heat during flowering reduce the number of flowers that can be pollinated effectively. Because each flower opens for only one day, missed opportunities cannot be recovered. Pod development reflects regional stability. Regions with consistent conditions support steady 8 to 9 month development. Regions with frequent storms or drought interruptions experience higher rates of pod loss or uneven development. These risks make vanilla production vulnerable to weather events. Cyclones, floods, or prolonged droughts can destroy vines or interrupt development for entire seasons. Recovery may take years because vines must regrow and rebuild reserves. This vulnerability contributes to regional concentration of vanilla production. Madagascar, for example, has become the largest producer because its climate supports vanilla growth despite periodic disruption. However, reliance on a few regions increases supply volatility. Price fluctuations reflect these regional constraints. When weather disrupts production in major growing areas, global supply drops. Because vanilla cannot be produced quickly, shortages persist until vines recover and mature. Regional labor practices also influence outcomes. In areas dominated by small-scale farming, hand pollination and careful curing remain central. In regions attempting larger-scale production, maintaining quality and consistency is more difficult. Cultural knowledge passed down through generations shapes how vanilla is grown in different regions. Techniques for pollination, pruning, and curing reflect local experience with climate and environment. This knowledge influences productivity as much as biological factors. Regional differences appear in cured vanilla as well. Pods from different regions vary in aroma profile, moisture content, and appearance. These differences reflect growing conditions, curing methods, and vine maturity rather than genetic variation alone. Local harvest timing also matters. Regions with predictable seasons allow coordinated harvesting and curing. Regions with variable weather require flexible timing, increasing labor demands and risk. The relationship between vanilla orchids and place is therefore intimate. The plant does not adapt quickly to new environments. Instead, Productivity relies on how closely local conditions resemble those of its native habitat, or how well growers can recreate them. Understanding regional influence explains why vanilla cultivation resists uniform industrialization. Each region requires tailored approaches to light, humidity, support, and labor. This place-specific behavior links vanilla orchids to broader ecological systems. The plant's success relies on forests, climate patterns, and human practices working together. Across regions, vanilla orchids demonstrate the same principles seen throughout their biology. Stability supports productivity. Variability introduces risk. The slower the plant grows, the more costly disruption becomes. By observing how vanilla orchids behave in different environments, it becomes clear that location shapes outcome. The vine records regional conditions in its growth, flowering, and pods. Each vanilla bean carries evidence of where it grew. Aroma, texture, and flavor reflect months of interaction with local temperature, humidity, and care. This regional signature sets the stage for understanding how vanilla connects ecology with economics and why its value fluctuates so widely. Vanilla orchids also shape and are shaped by the spaces they occupy. Their climbing habit, dependence on supports, and sensitivity to airflow create a close relationship between vine, structure, and surrounding environment. Over time, this relationship influences plant health, flowering success, and pod quality. Because vanilla orchids grow as long vines, space is not measured only by ground area. It is measured by vertical and horizontal pathways the vine can follow. Each bend, loop, and attachment point affects how energy moves and how stress is distributed along the plant. In forest settings, trees provide natural scaffolding. The vine climbs gradually, attaching itself to bark and branches. As it ascends, it encounters changing light levels, airflow, and humidity. These gradual shifts allow the plant to adjust without sudden stress. In cultivated settings, supports must recreate this gradual structure. Trellises, posts, or frames guide the vine upward before redirecting it horizontally. This pattern limits height while increasing productive length. The arrangement determines how evenly leaves receive light and how accessible flowers remain for pollination. Spacing between supports influences airflow. When vines are too close, humidity builds and air movement slows. This creates favorable conditions for fungal growth along shaded sections of the vine. Adequate spacing allows air to circulate, reducing moisture retention and disease risk. The way vines are looped or trained affects mechanical stress. Sharp bends restrict internal movement pathways and weaken tissues. Gentle curves distribute weight evenly and reduce strain at attachment points. Over time, these differences influence vine longevity and pod retention. As vines lengthen, weight accumulates. Developing pods add significant mass that must be supported for many months. If support structures flex or shift, repeated movement damages attachment points. Stable supports protect pods from breakage and reduce energy loss from repair. Airflow interacts with vine structure in subtle ways. Leaves exposed to moving air dry more quickly after rain or irrigation. Dry surfaces reduce fungal establishment. Stagnant air around dense loops traps moisture, increasing disease pressure. Light distribution also relies on structure. Leaves positioned too close together shade one another, reducing photosynthetic efficiency. Leaves spread along supports receive more even illumination. Balanced light supports steady sugar production along the vine. The vine's position affects flower accessibility. Flowers emerge at nodes along the vine and must be reachable for hand pollination. Poorly planned layouts force growers to stretch, climb, or disturb the plant, increasing the risk of damage during pollination. Well-designed systems place flowering sections at comfortable working height. This reduces handling stress and improves pollination success. Less disturbance during flowering supports better pod development later. Ground conditions beneath the vine influence the microclimate. Vegetation, mulch, or bare soil affect humidity near the lower vine. Moist ground increases local humidity, supporting hydration. Bare, dry ground reduces humidity and increases stress. However, excess moisture at ground level can increase disease risk. Good drainage prevents standing water that raises humidity too high. Ground cover must balance moisture retention with airflow. Vanilla orchids do not draw nutrients from soil, but soil conditions still matter. Organic debris on the ground decomposes and releases moisture into the air. This contributes to the humid environment the orchid relies on. Spacing between vines also affects disease containment. When one vine becomes infected, physical distance slows spread. Crowded vines allow pathogens to move quickly along shared supports or overlapping foliage. Over time, spatial arrangement shapes plant behavior. Vines trained in open, balanced layouts develop steadier growth and more consistent flowering. Crowded or poorly supported vines show uneven growth and reduced productivity. These effects accumulate slowly. A vine may tolerate suboptimal spacing for a season, but repeated stress weakens tissues and reduces flowering frequency. Long-term outcomes reflect early structural decisions. Human movement through the growing area influences outcomes as well. Frequent contact with vines transfers moisture and pathogens. Narrow pathways increase accidental damage. Wider access routes reduce disturbance and support careful management. The spatial rhythm of a vanilla plantation reflects the plant's needs. Supports are arranged to balance density with airflow. Vines are guided to create repeating patterns that support both growth and work. In regions prone to storms, spatial design becomes critical. Windbreaks reduce vine movement. Reinforced supports prevent collapse. These measures protect long-term investment by preserving vine integrity. The plant adjusts in response to these arrangements gradually. Leaves orient toward available light. Roots anchor where contact is strongest. Growth follows the pathways provided rather than resisting them. Over seasons, the vine adapts to its physical environment. Sections that receive consistent light and airflow become more productive. Less favorable areas contribute less. This selective productivity shapes overall yield. Spatial management also affects curing outcomes indirectly. Healthy vines produce pods that develop evenly, curing more consistently after harvest. Structural stability during growth influences final quality months later. Understanding space in vanilla cultivation goes beyond geometry. It involves anticipating how air, light, moisture, and human movement interact across seasons. The vine adjusts in response to this environment continuously. When space is managed well, the orchid's growth appears calm and deliberate. Vines extend steadily, flowers emerge predictably, and pods remain secure. When space is poorly managed, stress accumulates quietly until productivity declines. These spatial relationships explain why vanilla cultivation requires planning years in advance. Supports installed early determine how vines behave long after planting. Adjustments later are possible but costly. The vanilla orchid does not adapt quickly to sudden spatial change. Relocation, restructuring, or crowding forces the plant to redirect energy toward repair rather than production. Stability supports refinement rather than recovery. By observing how vanilla orchids interact with space, it becomes clear that structure is not secondary. It is part of the plant's biology. Growth follows the paths provided, and productivity relies on how those paths are shaped. Each vine records its spatial history in growth patterns, flowering nodes, and pod placement. This record reflects decisions made long before harvest. Understanding this relationship prepares the ground for examining how vanilla cultivation connects physical space with labor, time, and value. The vine's demands shape not only plant behavior, but human systems built around it. Vanilla orchids operate within narrow physical limits. Their measured growth, thin tissues, and dependence on consistent conditions mean that small shifts can have large effects. By looking at how the plant responds when conditions approach these limits, it becomes clearer why vanilla cannot be rushed and why consistency matters more than intensity. Temperature defines one of the most important boundaries. Vanilla orchids grow best when temperatures remain warm but not extreme. Within their preferred range, metabolic processes proceed steadily. Sugars move through the vine at predictable rates, tissues remain flexible, and growth continues without interruption. When temperatures rise too high, respiration increases. The plant consumes sugars faster to maintain basic cellular activity. Less energy remains available for growth, flowering, or pod development. Leaves may appear intact, but internal energy balance shifts away from reproduction. Excessive heat also increases water loss. Leaves and aerial roots lose moisture more quickly, especially when humidity drops. If water replacement cannot keep pace, tissues lose firmness and growth slows. Prolonged heat weakens vines and reduces flowering potential. Cold presents a different limit. Vanilla orchids are not adapted to low temperatures. When temperatures fall, metabolic activity slows sharply. Transport of water and sugars through the vine becomes inefficient. Extended cold damages tissues, leaving darkened or softened sections that recover slowly or not at all. Sudden temperature swings are especially stressful. Rapid shifts force the plant to adjust repeatedly, consuming energy that would otherwise support growth. Over time, frequent swings reduce productivity by diverting energy toward survival rather than development. Humidity sets another boundary. Vanilla orchids rely on moist air to support hydration through aerial roots. When humidity falls too low, roots dry and lose their ability to absorb moisture efficiently. Even if watering continues, the plant experiences internal water stress. Excess humidity creates problems as well. When air remains saturated without movement, moisture lingers on leaves, vines, and pods. These conditions support fungal growth. Disease becomes more likely, especially at joints and shaded areas where moisture collects. Airflow moderates this balance. Gentle air movement allows surfaces to dry gradually, reducing disease risk while maintaining humidity. Too little airflow traps moisture. Too much airflow dries tissues. The plant's tolerance lies between these extremes. Light availability also defines limits. Vanilla orchids require filtered light. Too much direct sun damages leaves, causing scorch and reducing photosynthetic capacity. Too little light limits sugar production, slowing growth and delaying flowering. The plant cannot compensate for poor light by increasing leaf area quickly. Growth is slow, and leaf replacement takes time. This makes light mismanagement costly, with effects lasting months or years. Water supply must remain steady but controlled. Vanilla orchids do not tolerate standing water. Saturated conditions rot roots and vine joints, interrupting anchorage and nutrient absorption. Conversely, irregular watering creates cycles of stress and recovery that weaken tissues. Nutrient balance sets another boundary. Vanilla orchids evolve to absorb small amounts of nutrients from organic debris rather than rich soil. Excess fertilization pushes rapid leaf growth that produces soft tissue vulnerable to disease. Insufficient nutrients limit repair and storage. Stress from any one factor often magnifies others. Heat stress increases water demand. Low humidity intensifies water loss. Poor airflow worsens disease risk under high humidity. These interactions narrow the safe operating range further. The timing of stress determines its impact. Stress during vine growth delays flowering. Stress during flowering reduces pollination success. Stress during pod development leads to pod loss or poor curing potential. Each stage has its own vulnerabilities. Because vanilla orchids develop slowly, Recovery from stress takes time. A vine damaged during pod development may not return to full productivity until the following year or later. Lost opportunities cannot be replaced quickly. This sensitivity explains why vanilla yields fluctuate widely. A single storm, drought, or disease outbreak can affect production for multiple seasons. The plant's biology does not allow rapid compensation. Management practices aim to keep conditions within tolerable ranges rather than maximizing growth. Shade moderates light and temperature, trellises stabilize structure, pruning improves airflow, watering supports humidity without saturation. Each practice addresses a specific limit. Variety selection also reflects these boundaries. Some vanilla strains tolerate slightly different conditions, but all share similar sensitivities. Genetic differences cannot overcome fundamental structural limits. Vanilla orchids can recover when stress is brief and conditions return to stability. Leaves regain firmness, growth resumes. Flowering potential rebuilds slowly as energy is stored again. However, repeated stress without recovery leads to decline. This balance between resilience and fragility defines vanilla cultivation. The plant can persist for many years when protected, but it cannot withstand constant pressure. Productivity relies on preventing stress rather than correcting it afterward. Understanding these limits clarifies why vanilla is grown in sheltered environments rather than exposed fields. Forest-like conditions buffer extremes and reduce the likelihood of crossing critical thresholds. It also explains why vanilla farming relies on observation. Subtle changes in leaf texture, color, or growth rate indicate approaching limits. Early adjustment prevents damage that would take years to repair. Vanilla orchids communicate stress quietly. Growth slows, leaves soften, flowers fail to appear. These signs reflect internal imbalance rather than visible collapse. By respecting these limits, growers maintain steady productivity. The goal is not rapid expansion, but sustained alignment between the plant's needs and its environment. Each vanilla pod represents success within narrow margins. Temperature, humidity, light, water, and care must align for months. When they do, the plant completes its cycle smoothly. When they do not, the opportunity is lost. These limits do not make vanilla fragile by accident. They are the result of a strategy that prioritizes efficiency over speed. The plant invests in slow, deliberate growth that rewards stability. Recognizing this strategy shifts how vanilla is approached. Instead of forcing production, cultivation focuses on maintaining balance. Productivity emerges as a consequence of restraint rather than pressure. This understanding prepares the ground for exploring how vanilla orchids interact with larger systems, including labor, time, and economic value. The plant's narrow tolerances shape not only growth, but the human systems built around it. Vanilla orchids show their long-term behavior most clearly when viewed across several years rather than a single harvest. Although pods develop slowly within one season, the plant's ability to continue flowering and producing relies on how well it manages energy storage, repair, and preparation from one cycle to the next. Each year begins with growth that relies partly on reserves built earlier. Leaves that formed in previous seasons continue to photosynthesize, supplying sugars to new vine sections and maintaining existing tissue. This overlap allows the plant to avoid starting from zero each season. Growth builds upon what already exists. As vines mature, energy storage becomes more efficient. Sugars move through familiar pathways along the vine and accumulate in older sections that remain structurally sound. These stored resources support flowering when conditions allow and buffer the plant against brief stress. Mature vines therefore tend to flower more reliably than young ones. Stress interrupts this accumulation. Heat, drought, disease, or physical damage reduces the amount of energy available for storage. When stress occurs repeatedly, reserves decline across seasons. The effects often appear later, as reduced flowering or fewer pods in subsequent seasons. This delayed response explains why vanilla production can vary widely from year to year, even when care appears consistent. A difficult season may not show its full impact until the following flowering cycle, when the vine lacks the reserves needed to initiate buds. Pruning decisions influence this long-term balance. Removing excessive vine length concentrates energy into remaining sections and shortens transport distance. When pruning is timed to follow growth rather than precede it, energy loss is minimized. Poorly timed pruning removes stored reserves and delays recovery. Training methods also shape multi-year outcomes. Vines guided gently along supports develop predictable growth patterns. Abrupt changes in direction or repeated repositioning force the plant to invest energy in repair rather than storage. Over time, consistent training supports steadier flowering. Environmental consistency plays a central role. Vanilla orchids benefit from stable humidity, temperature, and light across seasons. When these conditions remain within range year after year, the plant adapts its internal processes to match them. Growth becomes less reactive and more efficient. Sudden changes disrupt this adaptation. Shifts in shade, airflow, or watering routines require repeated adjustment. Each adjustment consumes energy that would otherwise support flowering or pod development. Over multiple years, this reduces productivity. As vines age, physical wear accumulates. Supporting heavy pods for many months strains attachment points along the vine. Without adequate support, older sections become vulnerable to breakage. Structural damage reduces productive length and increases recovery time. Disease pressure also accumulates across seasons. Even minor infections weaken tissues and interrupt energy transport. Repeated disease episodes shorten the productive lifespan of the vine. Preventative care becomes increasingly important as vines mature. Renewal strategies help manage aging. Allowing new vines to establish alongside older ones creates continuity while gradually replacing declining sections. Younger vines build reserves, while older vines continue producing, maintaining overall productivity. Spacing influences long-term health. Adequate spacing reduces disease pressure and allows each vine to receive sufficient light and airflow. Crowded conditions accelerate decline by increasing stress and competition for resources. Water management across seasons shapes longevity. Repeated cycles of drought, followed by recovery, gradually reduce efficiency. Stable moisture allows reserves to rebuild fully between demanding phases, supporting long-term productivity. Nutrient balance also affects aging. Moderate, consistent nutrition supports tissue repair and storage. Excess nutrients encourage rapid growth that weakens structure and increases disease risk. Deficiencies limit repair and reduce flowering potential. Vanilla orchids do not experience true dormancy, but growth slows during less favorable periods. These slow phases allow energy to accumulate, rather than being constantly spent. Vines that are allowed to rest resume growth more strongly than those pushed continuously. The timing of flowering across years reflects this balance. Vines that complete one season with strong reserves initiate flowers more readily the next year. Vines that finish depleted require additional time to rebuild before flowering again. Human management compounds these effects. Daily decisions accumulate over years. Consistent care reinforces stability. Inconsistent care introduces stress that reduces long-term output. Economic pressure often conflicts with biological needs. High demand encourages maximum harvesting, but overuse of the vine reduces future productivity. Sustainable cultivation balances immediate output with preservation of vine health. Observing vanilla orchids over multiple years reveals subtle indicators of balance. Leaf thickness, growth rate, and node spacing change gradually. These changes signal whether energy storage and repair are keeping pace with demand. Successful growers respond to these signals early. Adjustments are made before flowering declines significantly. This proactive approach preserves productivity rather than reacting to visible failure. The slow pace of vanilla growth makes recovery costly in time. Lost years cannot be replaced quickly. This reality shapes how cultivation decisions are made and why patience remains central. Over time, productive vines develop a rhythm. Growth, flowering, pod development, and recovery occur within predictable windows. This regularity reduces uncertainty and supports planning. Vanilla orchids reward long-term attention. Vines that are protected from extremes and allowed to build reserves improve rather than decline. Their productivity becomes steadier, even if total yield remains modest. This multi-year perspective explains why vanilla remains one of the most labor-intensive crops. Each vine represents years of investment. Care decisions made today shape outcomes far into the future. Understanding these long-term patterns prepares the ground for examining how vanilla production connects biological time with human systems of labor, value, and trade. Vanilla orchids follow a precise internal sequence across a single year, even though they do not experience a strict seasonal dormancy. Growth, flowering, pod development, and recovery occur in an ordered progression shaped by temperature, humidity, and energy availability. Each phase prepares the conditions for the next, and disruption at any point alters what follows. The cycle begins with active vegetative growth. Leaves expand along the vine, increasing surface area for photosynthesis. Sugars produced in these leaves support both continued growth and the maintenance of existing tissue. During this phase, the plant prioritizes extension and stabilization, strengthening attachment points and improving internal movement pathways. As leaf growth stabilizes, energy allocation begins to shift. When the vine has reached sufficient length and stored reserves are adequate, the plant becomes capable of initiating flower buds. This transition relies on accumulated readiness rather than a single environmental signal. Stable conditions across seasons allow this threshold to be reached. Flower initiation occurs at nodes along the vine. Buds remain small for weeks before developing further. During this period, the plant continues monitoring conditions. Stress from drought, heat, or disease can interrupt development and cause buds to abort, conserving energy for survival rather than reproduction. Once flowers open and pollination occurs, the plant enters a high-demand phase. Developing pods require steady delivery of water and sugars for many months. Leaves must remain active and healthy to meet this demand. Any reduction in photosynthesis directly affects pod growth and future flavor potential. During pod development, vegetative growth slows. The vine limits new extension and directs resources towards sustaining existing structures and pods. This restraint prevents overextension and reduces the risk of exhausting reserves before pod maturity. As pods approach full size, internal development nears completion. The plant gradually prepares for a shift away from reproduction. Energy that was previously directed into pod growth begins to be redirected towards storage within the vine. After pods are harvested, the plant enters a recovery phase. Leaves continue photosynthesis, but sugars are now stored rather than immediately used. This storage rebuilds reserves depleted during pod development and supports future flowering cycles. Runner growth may increase during this recovery phase if conditions allow. New vine sections begin forming, extending the plant's structure and creating future potential. If energy remains limited, runner growth is restrained, preserving reserves. Environmental conditions strongly influence recovery. Stable humidity and moderate temperatures allow efficient storage. Stress during this phase reduces the amount of energy that can be retained, weakening the plant's readiness for the next flowering cycle. growth slows during less favorable periods. While vanilla orchids do not enter true dormancy, cooler or drier conditions reduce metabolic activity. This slowdown allows the plant to conserve energy rather than expend it under marginal conditions. These slower periods function as rest phases. They are essential for rebuilding internal balance. Plants that are allowed to rest resume growth more effectively than those forced to remain active through constant intervention. The transition back into active growth relies on the success of this recovery. Vines with strong reserves resume leaf expansion and bud initiation more readily. Vines that finish the cycle depleted require additional time to rebuild before flowering again. Because vanilla orchids grow slowly, the effects of each phase are tightly linked. Poor recovery after harvest delays flowering. Weak flowering reduces pod development. Reduced pod development limits future energy storage. Each phase reinforces the next. This sequential dependency explains why vanilla production cannot be accelerated easily. Forcing one stage compromises others. Sustainable production relies on allowing each phase to complete its role fully. Management practices align with this sequence. After harvest, care focuses on supporting leaf health and storage rather than stimulating growth. During flowering, stability is prioritized over change. During pod development, protection and consistency matter most. Environmental disruptions alter this sequence. Storms, droughts, or disease events interrupt energy flow and delay transitions. Recovery requires time, and lost phases cannot be regained quickly. The plant's internal calendar is flexible but not forgiving. It adjusts timing in response to conditions, but it does not compress phases to compensate for loss. This characteristic underlies the long timelines of vanilla cultivation. Over successive years, this annual sequence becomes more predictable as the vine matures. Growth phases align more closely with local conditions. The plant's responses become less reactive and more measured. This predictability supports planning. Growers learn when flowering is likely, how long pod development will take, and when recovery must be protected. These expectations reduce risk and improve outcomes. Understanding the internal sequence of a vanilla orchid's year clarifies why patience is essential. Each stage relies on the completion of the one before it. Rushing disrupts balance rather than increasing output. The plant does not operate on a calendar imposed from outside. It follows internal readiness shaped by environment and past experience. Observing this readiness guides effective care. By respecting this internal sequence, growers align their actions with the plant's needs. This alignment allows the vine to progress steadily from growth to flowering to pod development and back again. Each cycle reinforces the plant's structure and internal pathways. Over time, these repetitions build efficiency rather than fatigue, provided stress remains within tolerable limits. This annual progression prepares the ground for understanding how vanilla orchids fit into larger systems that extend beyond the plant itself, including labor cycles, economic rhythms, and long-term ecological balance. Vanilla orchids function as integrated systems rather than a collection of separate parts. Leaves, aerial roots, vine tissue, flowers, and pods are linked by continuous movement of water, sugars, and signals. How efficiently these parts coordinate determines whether the plant maintains gradual growth or becomes strained. Water movement forms the backbone of this coordination. Moisture absorbed by aerial roots and surface tissues moves upward and inward through the vine. This flow supports cell expansion, nutrient transport, and temperature regulation. Because the vine is long and flexible, uninterrupted flow is essential. Any kink, break, or damaged section disrupts movement both above and below the injury. Sugar movement follows a parallel network. Sugars produced in the leaves travel through the vine to areas of demand. During vegetative growth, sugars support new leaf formation and vine extension. During flowering and pod development, sugars are redirected toward reproductive structures. During recovery, sugars are stored within vine tissue to support future growth. This redistribution happens continuously rather than in discrete steps. The plant adjusts in response to demand in real time. Developing pods draw resources steadily for months. When pods are absent, energy accumulates or supports new vine growth. This flexibility allows vanilla orchids to adjust without visible change, but it also means inefficiencies quickly affect outcomes. The crown area, where leaves, roots, and flowers originate, plays a central coordinating role. Although vanilla orchids lack a compact crown like strawberries, the junctions along the vine serve similar functions. Each node becomes a decision point, where energy is allocated to leaf growth, flower formation, or storage. Leaves differ in productivity depending on age and exposure. Mature leaves exposed to filtered light produce the most sugars. Very young leaves consume energy during formation, while older leaves gradually decline in efficiency. The balance of leaf ages along the vine affects overall energy availability. Airflow and light distribution influence this balance. Leaves that remain damp or shaded contribute less to sugar production and become more susceptible to disease. Well-spaced vines with even light support more uniform leaf function, improving coordination across the plant. Flowering adds complexity to coordination. Each flower represents a potential long-term commitment. When pollinated, it initiates months of pod development that draw resources continuously. The plant must assess whether it can support this demand without compromising survival. If energy supply is insufficient, flowers abort before opening or shortly afterward. This abortion is not failure, it is regulation. By limiting reproductive effort, the plant protects long-term stability. Once pods begin developing, coordination shifts. Sugar flow prioritizes pod growth over new vine extension. Leaves remain active to meet this demand, while new growth slows. This prioritization prevents overextension and reduces the risk of exhausting reserves. Roots respond in parallel. When sugar supply is strong, aerial roots remain active and attach firmly, supporting hydration and stability. When energy declines, root growth slows, reducing absorption capacity. This feedback loop influences the entire system. Temperature affects coordination by altering metabolic rates. Warm conditions increase demand for sugars and water. Cooler conditions slow transport and allow accumulation. These changes affect how quickly energy moves between parts. Humidity influences coordination as well. Adequate humidity supports root hydration and leaf firmness. Low humidity increases water loss, forcing the plant to conserve resources and reduce growth. Disease disrupts coordination by damaging tissues involved in transport. Infected sections become barriers, forcing energy to reroute or halting movement entirely. This is why early disease control preserves overall function rather than simply removing visible damage. Pruning alters coordination deliberately. Removing sections of vine reduces demand and shortens transport distances. When done carefully, pruning improves efficiency by focusing energy where it is most effective. Poor pruning removes stored reserves and increases strain elsewhere. Structural support influences coordination indirectly. Stable supports reduce movement and mechanical stress, protecting internal pathways. Unstable supports cause repeated strain, diverting energy toward repair rather than growth or reproduction. As vines age, coordination becomes more refined. Repeated cycles strengthen internal pathways and improve predictability. Mature vines distribute resources more efficiently than young ones, provided damage and disease are controlled. However, excessive age introduces complexity. Too many nodes compete for resources, reducing efficiency. Renewal restores simpler coordination by replacing older sections with new growth. Human management interacts with this system constantly. spacing, pruning, watering, and shade management all influence how resources move through the plant. Each decision affects coordination rather than acting in isolation. The plant's appearance reflects coordination status. Even leaf color, gradual growth, and consistent pod development indicate balanced flow. Uneven growth, leaf drop, or pod loss indicate disrupted coordination. Because vanilla orchids grow slowly, coordination issues persist. Problems do not resolve quickly without intervention. Conversely, improvements require patience before results appear. This slow feedback reinforces the importance of observation. Changes in coordination must be identified early to prevent long-term impact. Subtle signs matter more than dramatic symptoms. Over time, well-coordinated vines appear calm. Growth is steady, flowering predictable, and recovery complete. Poorly coordinated vines appear strained, with uneven growth and inconsistent production. Understanding coordination clarifies why vanilla cultivation resists mechanization. Each vine behaves as a unique system shaped by its own structure and history. Standardized treatment cannot account for these differences. Successful cultivation aligns human actions with the plant's internal logic. Supporting coordination allows the vine to express its full potential without forcing growth. This internal network of movement and balance explains how a single vine can sustain production over many years. The plant does not rely on speed or strength, but on efficient coordination across all parts. As the story continues, this coordination extends beyond the plant itself, connecting vanilla orchids to wider ecological and human systems that depend on their slow, deliberate rhythm. Vanilla orchids change gradually as they age, and these changes influence how the vine grows, flowers, and sustains production across seasons. Age does not bring an abrupt shift. Instead, it alters efficiency, structure, and recovery in small increments that accumulate across seasons. Observing these changes helps explain why older vines often behave differently from younger ones, even under the same conditions. Young vanilla vines focus most of their energy on expansion. Leaves form quickly, attachment points strengthen, and the vine extends to occupy available space. During this stage, internal movement pathways are still developing. Sugars and water move effectively, but storage capacity remains limited. Flowering is uncommon because the plant prioritizes building length and stability. As the vine matures, internal efficiency improves. Repeated movement of water and sugars along the same pathways strengthens transport tissues. This reduces resistance within the vine and allows resources to be delivered more reliably to nodes capable of flowering. Mature sections of vine therefore support reproduction more effectively than newly formed growth. Flowering frequency often increases with maturity. Older vines possess larger stored energy and a more predictable internal rhythm. When environmental conditions align, these vines initiate flowers more readily because the cost of reproduction can be met without compromising survival. However, maturity also introduces complexity. Each additional node represents a potential demand for resources. As nodes accumulate, competition increases. Without management, this internal competition reduces efficiency, leading to fewer flowers or smaller pods despite adequate external conditions. Structural wear becomes more relevant as vines age. Years of supporting heavy pods strain attachment points along the vine. Repeated bending, handling, and environmental exposure weaken tissues across seasons. Without reinforcement or pruning, older sections become vulnerable to breakage. Disease risk also increases with age. Even when infections are controlled, repeated minor damage leaves scars within tissues. These scars interrupt smooth transport and reduce overall efficiency. Older vines therefore require more careful monitoring to maintain productivity. Pruning plays a central role in managing age-related change. Removing unproductive or damaged sections simplifies the vine's internal structure. This reduces competition among nodes and shortens transport distances. Well-timed pruning restores efficiency rather than reducing potential. The timing of pruning matters. Pruning immediately after active growth or pod harvest preserves stored energy while redirecting resources. Pruning during stress or before flowering removes reserves needed for reproduction and delays recovery. Training older vines also affects aging outcomes. Vines that are gently repositioned maintain flexible tissues and stable attachment. Vines forced into sharp angles or repeatedly adjusted develop stress points that weaken across seasons. Environmental stability becomes increasingly important as vines age. Younger vines tolerate variability more easily because growth capacity remains high. Older vines rely on efficient maintenance rather than rapid repair. Fluctuating conditions accelerate decline by increasing energy demands that cannot be met easily. Humidity, temperature, and light must remain within narrow ranges to support older vines. Small deviations that younger plants might tolerate cause larger impacts in mature vines. This sensitivity reflects reduced redundancy in internal systems. Nutrient balance also shifts with age. Mature vines require steady but modest nutrient supply. Excess nutrients push soft growth that stresses older tissues. Insufficient nutrients limit repair and storage, increasing vulnerability to disease. Water management must be consistent. Older vines respond poorly to repeated cycles of drought and recovery. Stable moisture supports continued function of aerial roots and internal movement pathways tissues. Age influences recovery speed. Younger vines rebound quickly from stress because growth capacity remains high. Older vines recover more slowly, relying on stored energy rather than new growth. This slower recovery makes prevention more important than correction. Renewal strategies help manage aging. Allowing new vines to establish alongside older ones creates overlap. Younger vines begin building reserves, while older vines continue producing. Over time, older sections can be removed, without sudden loss of productivity. This staged renewal prevents gaps in production. It also reduces risk by spreading dependency across vines at different life stages. Each vine contributes according to its capacity rather than being pushed beyond it. In unmanaged systems, aging leads to gradual decline. Flowering becomes irregular, pods develop unevenly, and disease becomes more frequent. These changes occur slowly, making them easy to overlook until productivity drops significantly. Recognizing early signs of aging allows timely intervention. Reduced leaf firmness, uneven growth, or declining pod size indicate that internal efficiency is decreasing. Addressing these signs through pruning, support, or renewal restores balance. Aging does not represent failure in vanilla orchids. It represents the natural outcome of long-term growth under limited structure. The plant's strategy favors slow accumulation rather than perpetual expansion. Vanilla orchids are not built for constant replacement. They are built for continuity with periodic renewal. Respecting this pattern allows vines to remain productive for many years rather than exhausting them prematurely. Human expectations often conflict with this biology. High demand encourages pushing vines to maximum output. This approach shortens productive lifespan. Sustainable cultivation balances present yield with future capacity. As vines age gracefully under consistent conditions, their behavior becomes predictable. Flowering occurs within expected windows. Pod development proceeds steadily. Recovery follows without interruption. This predictability supports planning and reduces stress. The relationship between age and productivity in vanilla orchids highlights the importance of patience. Time strengthens internal systems when conditions remain supportive. Rushing undermines those gains. Understanding aging prepares the ground for examining how vanilla orchids fit into broader systems that extend beyond the plant itself. Their long lifespan connects biological time with human labor, economic cycles, and ecological stability. Age, in this context, becomes a measure of refinement rather than decline. Each season adds experience to the vine's internal structure. When supported properly, that experience translates into steady, reliable production rather than diminishing returns. Vanilla orchids also reflect the cumulative impact of human care across seasons. Because the plant grows slowly and commits to long development cycles, management decisions shape outcomes years after they are made. Planting, training, pruning, watering, and daily handling all influence how the vine allocates energy and how long it remains productive. Planting location establishes the baseline. Vanilla orchids placed in sheltered environments with stable humidity and filtered light begin growth with fewer constraints. Locations exposed to strong wind, direct sun, or rapid drying impose stress that the plant must compensate for continuously. This compensation consumes energy that would otherwise support flowering and pod development. Support design is one of the most influential decisions. The type, spacing, and stability of supports determine how the vine grows and how stress is distributed along its length. Supports that allow gradual climbing and horizontal training encourage flowering and reduce mechanical strain. Weak or unstable supports increase movement, damaging attachment points and interrupting internal movement pathways. Training practices influence long-term efficiency. Vines guided gently into consistent patterns develop predictable growth. Abrupt redirection forces the plant to repair tissue and reallocate energy. Over time, repeated disruption reduces flowering frequency and pod quality. Pruning decisions accumulate in similar ways. Removing excess length after growth concentrates energy into productive sections. Removing too much tissue removes stored reserves. Careful timing preserves energy while improving airflow and light penetration. Poor timing delays recovery and reduces readiness for flowering. Water management has long-lasting effects. Vanilla orchids require steady moisture without saturation. Consistent watering supports continuous internal flow. Irregular watering introduces cycles of stress and recovery that weaken tissues across seasons. Because recovery is slow, repeated inconsistency compounds damage. Humidity management works alongside watering. Maintaining ambient humidity reduces reliance on direct watering and supports aerial root function. Sudden drops in humidity force the plant to close stomata and reduce growth. Restoring humidity takes time, and repeated fluctuations reduce overall efficiency. Light management must remain stable. Gradual adjustments allow leaves to adapt. Sudden increases in light intensity damage tissue and reduce photosynthetic capacity. Sudden decreases limit energy production. Consistency supports gradual growth and predictable flowering. Nutrient practices shape tissue quality. Vanilla orchids evolve to absorb small amounts of nutrients from organic debris. Heavy fertilization pushes rapid growth that produces soft tissue vulnerable to disease. Balanced minimal nutrition supports strength and longevity rather than speed. Handling during flowering and pod development requires restraint. Excessive contact transfers moisture and pathogens. Movement damages delicate tissues. Careful handling preserves flower viability and pod attachment, supporting successful development. Pollination practices are especially sensitive. Each flower opens once, and successful pollination relies on precise timing and technique. Rushing increases damage. Delays miss the opportunity entirely. Experience improves efficiency, but conditions still dictate success. Harvest timing reflects cumulative care. Pods harvested at proper maturity cure more evenly and produce better flavor. Early harvesting interrupts internal development. Late harvesting risks splitting or decay. These outcomes reflect decisions made months earlier during pod growth. Curing practices extend the influence of management beyond the vine. The quality of curing determines how well the plant's chemical potential is expressed. Inconsistent curing wastes months of biological effort. Careful curing completes the process initiated by the plant. Sanitation affects long-term health, removing plant debris, fallen leaves, and damaged pods reduces disease pressure. Clean tools prevent pathogen transfer. Neglect allows pathogens to accumulate, increasing risk with each season. Human traffic around vines influences outcomes. Frequent contact compacts surfaces, transfers moisture, and causes accidental damage. Clear pathways and deliberate movement reduce disturbance and support stability. Management consistency matters more than intensity. Small, regular adjustments maintain alignment. Large interventions introduce shock. The plant responds better to steady care than to dramatic correction. Economic pressure can distort management choices. High market demand encourages maximizing output. Pushing vines beyond their capacity reduces future productivity. Sustainable management accepts moderate yields in exchange for long-term stability. Timescale defines success in vanilla cultivation. Decisions made today affect flowering years later. Mistakes persist because the plant cannot recover quickly. This long feedback loop rewards patience and penalizes haste. Vanilla orchids respond clearly to good management. Leaves remain firm. Growth is even. Flowering occurs reliably. Pods develop steadily. These signs indicate internal balance supported by consistent care. Poor management produces equally clear signals. Growth becomes uneven. Leaves soften. Flowering declines. Pods abort. These changes reflect cumulative imbalance rather than single events. Understanding this accumulation clarifies why vanilla farming remains labor-intensive. Each vine requires individual attention over many years. Mechanization cannot replace observation and timing. Successful growers develop routines that align with the plant's rhythm. Tasks are performed at predictable times. Interventions are measured. This rhythm reduces error and supports steady productivity. Management does not force vanilla orchids to perform. It creates conditions that allow performance. The plant does the rest at its own pace. Over multiple seasons, vines managed with restraint outperform those pushed aggressively. Productivity remains stable rather than peaking and collapsing. Quality improves rather than fluctuating. The vanilla orchid therefore reflects the character of its care. The vine's condition mirrors the consistency, patience, and attention it receives. Each pod represents not only biological success, but accumulated management decisions. This relationship prepares the ground for examining how vanilla connects to wider human systems, including labor organization, economic value, and global trade. The plant's slow rhythm shapes everything built around it. Vanilla orchids reveal their resilience most clearly in how they recover from disruption. Although the plant grows slowly and commits energy over long periods, it is capable of gradual repair when conditions improve. Recovery in vanilla is not fast or dramatic. It unfolds quietly through restored balance in water movement, energy flow, and tissue stability. Short-term stress often begins with changes in moisture or temperature. When humidity drops or temperatures rise sharply, leaves lose firmness and reduce transpiration. This response limits water loss, but also slows nutrient and sugar movement through the vine. Growth pauses as the plant shifts from expansion to preservation. When conditions stabilize, recovery begins. Moist air restores hydration to aerial roots. Leaves regain turgor pressure, and transpiration resumes. As water movement increases, dissolved nutrients travel more freely through the vine. This renewed flow supports gradual repair rather than rapid regrowth. Energy reserves stored in the vine play a central role during recovery. Older sections of vine release stored sugars to support damaged tissues. This process allows the plant to repair without producing large amounts of new growth. Repair takes priority over expansion because replacing tissue is more efficient than rebuilding structure entirely. Heat stress follows a similar pattern. Elevated temperatures increase respiration, consuming sugars faster than they are produced. When temperatures moderate, respiration slows and sugars accumulate again. Recovery relies on how much energy remains available after the stress period. Brief heat waves leave little lasting damage. Prolonged heat reduces reserves and lengthens recovery time. Physical damage creates more complex recovery challenges. Broken or crushed vine sections interrupt transport pathways. Energy cannot bypass these breaks easily. Removing damaged sections prevents further loss, but it also shortens the vine and reduces stored energy. Recovery after physical damage, therefore, requires time to rebuild transport efficiency. Disease-related damage slows recovery further. Fungal infections damage tissues responsible for water and sugar movement. Even after infected sections are removed, surrounding tissue must adjust to altered flow patterns. This adjustment happens gradually as new pathways strengthen. Recovery is influenced strongly by timing. Stress during active growth delays vine extension and flowering readiness. Stress during pod development diverts energy away from repair, prolonging weakness. Stress during recovery phases reduces storage, weakening future resilience. Because vanilla orchids lack true dormancy, recovery relies on slowed activity rather than complete rest. During cooler or drier periods, growth reduces naturally. These slow phases allow energy to accumulate rather than being consumed by constant growth or reproduction. Environmental stability during recovery is more important than improvement speed. Gradual restoration of humidity, temperature, and light allows tissues to adjust without additional stress. Rapid changes, even if favorable, force repeated adjustment and consume energy needed for repair. Airflow supports recovery by reducing disease risk. Leaves and vines that dry evenly resist secondary infection. Clean airflow prevents moisture from lingering on damaged tissue, reducing complications during healing. Nutrient balance must be maintained carefully during recovery. Excess nutrients push new growth before tissues are ready, producing soft, vulnerable sections. Insufficient nutrients slow repair. Balanced, minimal feeding supports tissue strengthening without forcing expansion. Pruning decisions during recovery must be conservative. Removing too much tissue reduces stored energy and delays repair. Targeted removal of damaged or unproductive sections shortens transport distance while preserving stored energy in healthy vine segments. Support structures influence recovery outcomes. Stable supports reduce movement that would otherwise strain healing tissues. Vines secured gently experience less mechanical stress, allowing internal repair to proceed uninterrupted. Recovery in vanilla orchids is uneven along the vine. Sections closer to stored reserves recover faster. Younger growth recovers more slowly because it relies on transport from older sections. This uneven recovery shapes future growth patterns and influences where flowering resumes. Repeated stress without recovery leads to cumulative decline. Each episode reduces reserves and damages transport pathways. Over time, the vine becomes less responsive to improvement. Recognizing early signs of stress prevents this progression. Vanilla orchids communicate recovery status through subtle cues. Leaves regain firmness and even color. Growth spacing becomes regular. New leaf emergence resumes gradually. Absence of these signs indicates incomplete recovery. Human management plays a decisive role during recovery, reducing intervention, stabilizing conditions, and allowing time supports restoration. Attempts to accelerate recovery often prolong it by adding stress. Because recovery is slow, patience becomes a practical requirement. Vines that are given time to repair often return to productivity. Vines pushed prematurely remain weak and vulnerable. Recovery also influences future flowering. Vines that complete recovery with restored reserves initiate flowers more reliably in the following cycle. Vines that remain depleted delay flowering to prioritize survival. This delayed response explains why recovery efforts may not show immediate results. Improvements made today affect flowering months or years later. Understanding this timeline prevents misinterpretation of outcomes. Vanilla orchids are resilient within limits. They do not recover from severe damage quickly, but they do recover from moderate stress when stability returns. This resilience relies on the preservation of structure rather than replacement. The plant's recovery strategy favors conservation over speed. Repair occurs by reinforcing existing tissues rather than producing new ones. This approach preserves long-term function but requires time. As recovery progresses, growth resumes gradually. New leaves appear. Transport efficiency improves. The vine returns to its steady rhythm without visible urgency. This quiet recovery reflects the broader pattern of vanilla growth. The plant advances through slow accumulation rather than rapid change. Each improvement builds on what remains rather than replacing what was lost. Understanding recovery clarifies why vanilla cultivation emphasizes prevention. Avoiding stress reduces the need for repair. When stress does occur, supporting recovery preserves future productivity. Each period of recovery strengthens the vine's internal systems when allowed to complete fully. Over time, vines that recover properly become more stable and less reactive. Vanilla orchids do not overcome disruption by force. They restore balance by waiting for conditions to settle. This approach turns patience into resilience. Vanilla orchids develop a distinct sense of familiarity with their surroundings across seasons. As vines remain in the same environment across repeated cycles of growth and recovery, their responses become more efficient. The plant expends less energy, adjusting, and more energy, maintaining steady function. This settling process supports consistent flowering and pod development when conditions remain stable. Roots and aerial attachment points play a key role in this familiarity. Aerial roots repeatedly anchor in the same locations, pressing against bark, supports, or trellis surfaces. Over time, these contact points become reliable pathways for moisture absorption and stability. When humidity and airflow remain predictable, roots function without interruption. The vine's internal movement pathway system adapts as well. Water and sugars move along roots that have been used repeatedly. Transport tissues become more efficient, reducing resistance and energy loss. This efficiency allows mature vines to support flowering with less strain than younger vines. Leaf placement reflects repeated exposure to light. Leaves that consistently receive filtered light grow larger and remain active longer. Shaded or stressed positions contribute less. Over seasons, the vine favors growth in areas that support efficient photosynthesis, reinforcing productive zones. Flowering becomes more regular under familiar conditions. Vines exposed to predictable temperature and humidity patterns initiate flowers within a narrower window. Pollination efforts become more efficient because flowering timing stabilizes. This regularity improves the chances of successful pod development. Energy allocation also becomes more predictable. During flowering and pod development, sugars are directed toward reproductive structures. During recovery, sugars return to storage within older vine sections. Because these transitions follow familiar patterns, the plant avoids excessive redirection that would otherwise consume energy. Runner growth in vanilla is limited compared to ground plants, but new vine sections still emerge. Under familiar conditions, vine extension occurs steadily, without sudden surges. This controlled growth supports long-term structure without overwhelming existing support systems. Water use stabilizes as well. Vines acclimated to local humidity regulate transpiration more effectively. Leaves open and close, stomata in response to known patterns, rather than reacting sharply to each change. This reduces water stress during brief fluctuations. Temperature patterns reinforce this familiarity. In environments with consistent seasonal progression, vines align growth timing accordingly. Cooler periods slow activity, warmer periods support growth. The plant no longer treats these changes as threats but as expected phases. This does not eliminate vulnerability. Extreme heat, prolonged drought, or severe disease still disrupt growth. However, vines that have settled into supportive environments recover more readily because their internal coordination is already aligned with local conditions. Human management interacts with this settling process. Consistent care reinforces familiarity. Stable watering routines, predictable pruning schedules, and steady shade management allow the vine to refine its internal responses. Abrupt changes force reallocation of energy and temporarily reduce efficiency. The visible form of the vine reflects this settled state. Growth spacing becomes regular. Leaves show even size and color. Flowering nodes appear in predictable positions. These signs indicate that the plant is operating within conditions it understands and can manage. This stability supports long-term productivity. Rather than alternating between heavy output and exhaustion, settled vines produce moderate but reliable yields across seasons. Pods develop evenly, and recovery follows without delay. As vines age, familiarity becomes more important. Older vines rely on efficiency rather than rapid growth. When conditions remain predictable, these vines maintain function longer. When conditions fluctuate widely, decline accelerates. The surrounding environment responds as well. Pollination schedules align more closely with flowering. Soil organisms and microflora stabilize around consistent moisture and debris patterns. These interactions reinforce stability at a small scale. Across seasons, familiarity reduces the cost of growth. The plant spends less energy responding to surprise and more energy sustaining productive processes. This efficiency improves resilience and reduces vulnerability to moderate stress. Vanilla orchids illustrate how repetition shapes biological systems. Repeated exposure to the same conditions allows the plant to refine its responses. Growth becomes less reactive and more measured. This refinement explains why vanilla vines often perform better after their first full flowering cycle. Initial establishment requires adjustment. Once roots, vine, and leaves have experienced repeated cycles, subsequent growth aligns more closely with the environment. When familiarity is disrupted, efficiency drops. Transplanting, major restructuring, or abrupt climate changes force the plant to rebuild internal patterns. During this adjustment period, flowering and pod quality often decline temporarily. Given time, new patterns form. Roots re-anchor, transport pathways adjust, leaves adapt to light and humidity. Efficiency returns gradually as the vine relearns its environment. This process highlights the value of stability in vanilla cultivation. Flexibility allows recovery, but stability allows refinement. The best outcomes occur when vines remain in conditions that suit them over long periods. Understanding familiarity helps explain why vanilla production resists rapid relocation or industrial scaling. Each vine develops a relationship with its environment that cannot be transferred instantly. Over time, the vine's behavior reflects this relationship. Growth, flowering, and recovery settle into a rhythm shaped by experience, rather than constant adjustment. This rhythm supports calm, steady productivity. The vine grows without urgency, flowers when conditions align, and recovers without strain. Vanilla orchids are often described as slow-growing, but their long-term success relies on this quiet process of settling in. Once familiarity is established, the plant becomes less fragile and more reliable. Each season reinforces this pattern. Leaves grow where light is most supportive. Roots function where humidity is stable. Flowers form where energy flow is reliable. The vine's structure becomes a record of what has worked. Through familiarity, vanilla orchids balance responsiveness with efficiency. They remain sensitive to change, but they are not constantly strained by it. This balance allows them to produce consistently without exhausting their limited structure. Vanilla orchids are easier to understand when their behavior is viewed as a single connected system rather than a series of separate events. Growth, flowering, pod development, recovery, and aging are not independent phases. Each relies on the same physical structures moving water, sugars, and energy through a long, flexible vine over extended periods of time. The structure of the vine establishes these limits from the beginning. Vanilla orchids grow as elongated, climbing stems supported by external structures. This design reduces the need for thick, woody tissue, but it also limits how quickly resources can be moved and how much strain the plant can tolerate. Energy must travel along the length of the vine to reach growing points, flowers, and developing pods. Aerial roots support this system by anchoring the vine and absorbing moisture from the surrounding environment. These roots function best when humidity remains high and airflow is gentle. Because they are exposed, they respond immediately to changes in air moisture. When conditions are stable, hydration remains steady. When conditions fluctuate, water movement slows, and the entire system feels the effect. Leaves provide the primary source of energy. Broadleaf surfaces capture filtered light and convert it into sugars through photosynthesis. These sugars move through the vine to support all active processes. Leaf position and health determine how much energy enters the system at any moment. Leaves damaged by heat, disease, or poor light reduce supply across the entire vine. Flowering occurs only when this system reaches sufficient readiness. Years of gradual growth allow transport pathways to strengthen and stored energy to accumulate. Flower buds form at nodes along the vine only when the plant can support months of future demand. This restraint prevents the vine from committing resources it cannot sustain. The one-day flower window reflects this strategy. Rather than flowering continuously, the vanilla orchid concentrates reproduction into brief periods that align with internal readiness and environmental stability. This limits exposure to risk while preserving the ability to reproduce when conditions are favorable. Pollination links the plant's internal system to external action. In native habitats, specialized bees complete this process. In cultivation, human hands replace that role. Each successful pollination initiates a long developmental commitment that cannot be reversed easily once begun. After pollination, pod development extends demand across many months. Water and sugars must flow steadily into the developing capsule. Because the pod grows slowly, consistency matters more than intensity. Short disruptions may be tolerated, but repeated stress alters internal structure and reduces curing potential later. During this phase, the plant does not attempt to increase growth elsewhere. Vine extension slows, and energy is directed towards sustaining existing structures. This prioritization prevents exhaustion and protects long-term function. The absence of aroma during pod growth reflects this focus. Chemical precursors are formed and stored, but fragrance does not develop until curing. This separation allows biological development to complete before chemical transformation begins. The plant's role ends with structural readiness rather than sensory expression. Curing completes what growth prepared. Enzymes activated after harvest transform stored compounds into aroma over weeks and months. This process depends entirely on pod maturity and internal structure shape during vine development. Flavor, therefore, reflects the full history of the plant, rather than a single stage. Aging emerges naturally from repeated cycles of this coordination. As vines mature, transport efficiency improves and energy storage increases. At the same time, complexity builds as nodes accumulate. Without renewal, internal competition reduces efficiency. With careful management, maturity enhances reliability rather than limiting output. Recovery links cycles together. After flowering and pod harvest, leaves redirect sugars back into the vine. This storage phase rebuilds reserves needed for future flowering. Because growth is slow, recovery must be protected rather than accelerated. Environmental sensitivity runs through every stage. Temperature affects respiration and sugar balance. Humidity affects hydration and disease risk. Light controls energy input. Airflow moderates moisture and heat. Because the system is compact, changes propagate quickly. This sensitivity explains why vanilla orchids reward stability. When conditions remain within narrow ranges, internal coordination improves. Growth becomes predictable. Flowering aligns with expectation. Recovery completes fully. Management succeeds when it supports this integration. Gentle training preserves transport pathways. Pruning simplifies structure without removing reserves. Shade moderates light without starving leaves. Watering supports humidity without saturation. Each practice protects internal balance. Disease and damage disrupt integration by interrupting flow. Prevention preserves coordination more effectively than repair. Because recovery is slow, avoiding disruption carries greater value than correcting it afterward. Economic factors intersect with this biology. Long timelines, precise labor, and vulnerability to disruption limit rapid expansion. These constraints shape supply and value. The plant's biology determines the pace of systems built around it. Across regions, the same integrated system responds differently to local conditions. Stable climates support steady production. Variable environments introduce risk. Each location leaves a signature on vine behavior and pod quality. Over time, the vanilla orchid becomes a record of alignment. Growth reflects how well internal coordination matched environmental support. Pods represent the outcome of sustained balance rather than isolated effort. The plant does not maximize growth, flowering, or yield independently. Growth supports flowering only when reserves allow. Flowering proceeds only when pod development can be sustained. Recovery limits future commitment until balance is restored. Each function constrains the others within what the vine can physically support. This slow pace explains why vanilla develops value through continuity rather than abundance. Leaves produce sugars steadily rather than rapidly. Pods mature over months rather than weeks. Productivity emerges from repeated stability rather than speed. Because the system is fully connected, disruption in one area affects the whole. Damage to leaves reduces energy input. Damage to the vine interrupts transport. Damage to roots or attachment points reduces hydration. Repair requires restoring flow across the entire system. This takes time. As cycles repeat across seasons, internal pathways strengthen. Transport becomes more efficient. Energy storage and release become predictable. Growth responses become measured rather than reactive. Productivity stabilizes because the plant no longer compensates for imbalance. Seen this way, the vanilla orchid is not fragile by accident. Its sensitivity limits overextension. The plant produces only when conditions support completion of the entire cycle, from flowering through pod development and recovery. This understanding prepares the ground for the final chapters, where the slow biology of the vanilla orchid connects directly to human labor, timing, and systems built around patience rather than acceleration. Vanilla orchids also reveal how biological time intersects with human labor. The plant's measured growth and narrow flowering window require daily attention over many years. This interaction shapes not only how vanilla is grown, but how work, timing, and responsibility are organized around it. Because vanilla orchids flower only once per year, and each flower opens for a single day, pollination demands precise observation. Growers must inspect vines daily during the flowering season. Missed flowers cannot be recovered. This creates a rhythm of work defined by attentiveness rather than speed. Hand pollination requires coordination between plant readiness and human presence. Flowers open gradually across the vine, rather than all at once. Labor must be distributed across days or weeks, matching the plant's pace. Concentrated effort on a single day is ineffective because flowers do not cooperate with fixed schedules. This dependence on timing extends through pod development. After pollination, pods require months of monitoring. Vines must be checked for disease, damage, or stress that could interrupt development. Each pod represents a long commitment of care rather than a quick return. Because pods develop slowly, labor cannot be postponed. Delayed intervention allows small problems to compound. Disease spreads quietly, supports weaken, environmental stress accumulates. The cost of inattention grows with time because recovery is slow. Harvest timing reflects the same discipline. Pods must be picked when internal development is complete, but before splitting or degradation begins. This moment varies by vine and by pod. Harvest therefore relies on judgment, rather than uniform timing. Curing extends labor further. The process unfolds over months and requires repeated handling. Pods are heated, wrapped, unwrapped, dried, and inspected. Each step relies on moisture level, temperature, and aroma development. Errors at this stage cannot be corrected later. This extended timeline links vanilla production to patience. Work is spread across years rather than seasons. Success relies on consistency rather than intensity. Labor cannot be rushed because biological processes do not accelerate under pressure. These constraints shape who can grow vanilla successfully. Small-scale growers with the ability to monitor vines closely often outperform larger operations. Attention replaces machinery. Skill replaces speed. The economic value of vanilla reflects this labor structure. High prices are not driven by rarity of land or inputs, but by time and care. Each pod embodies years of observation, manual pollination, and controlled curing. Price volatility also follows from biological constraints. A poor flowering season or storm affects supply for years rather than months. Because vines take time to recover, shortages persist even after conditions improve. This vulnerability affects growers' decisions, maintaining reserves, diversifying income, and renewing vines gradually reduce risk. Pushing vines for maximum output increases short-term returns but weakens future capacity. The relationship between labor and plant biology shapes knowledge transmission. Vanilla cultivation techniques are often passed down through generations. Timing cues, pruning habits, and curing methods reflect accumulated experience rather than written instruction. This knowledge remains local. Techniques that succeed in one region may fail in another because environmental timing differs. Local growers learn to read subtle signals in leaf texture, growth spacing, and flower readiness that indicate when action is required. Labor patterns follow seasonal cues rather than calendar dates. Flowering does not occur on demand. It adjusts in response to accumulated readiness. Workers adjust schedules to the plant, rather than forcing the plant to conform. This flexibility contrasts with industrial agriculture, where crops are synchronized for efficiency. Vanilla resists this model. Its biology imposes irregularity, requiring adaptive human systems. Over time, this interaction shapes landscapes. Support structures, shade trees, and pathways reflect the need for daily access. Farms are designed for careful movement rather than large machinery. The slow pace of vanilla cultivation also affects decision-making. Investments must be planned years ahead. Mistakes persist. Success accumulates slowly. This timeline discourages speculative expansion and rewards steady stewardship. The human experience of working with vanilla mirrors the plant's rhythm. Attention replaces urgency. Observation replaces force. Progress is measured in seasons rather than days. This alignment fosters resilience. Growers accustomed to long timelines are less reactive to short-term fluctuations. They manage uncertainty by maintaining stability rather than chasing immediate gain. The vanilla orchid therefore connects biology with human organization. Its growth shapes labor schedules, economic planning, and social knowledge. The plant's needs ripple outward into systems built around patience. As vines mature, labor demands stabilize. Flowering becomes more predictable. Curing routines become refined. Experience reduces error. Productivity steadies rather than spikes. This maturity benefits both plant and grower. The vine operates within its limits. The grower works within the plant's rhythm. Neither is pushed beyond capacity. Understanding this relationship clarifies why vanilla remains one of the most labor-intensive crops. It cannot be automated without loss of quality. Each step requires judgment, shaped by long familiarity. This labor-intensive structure also explains why vanilla connects strongly to place. Skills are adapted to local conditions. Timing reflects local climate. Value reflects local effort. Through this lens, vanilla production becomes a collaboration rather than extraction. The plant sets the pace. Humans respond with attention and care. This collaboration prepares the way for the final chapter, where the slow, interconnected rhythms of the vanilla orchid resolve into continuity rather than completion. Vanilla orchids reach a point where their patterns of growth, response, and recovery are well established. By this stage, the vine's structure reflects years of interaction with light, humidity, temperature, and careful handling. Growth no longer accelerates. Instead, it follows familiar pathways that have proven stable across repeated cycles. At maturity, the vine's internal movement pathways becomes efficient. Water and sugars move along reinforced roots that have carried the same flows season after season. Leaves maintain steady output without pushing excess growth. Nodes that have supported flowers before continue doing so when conditions allow. Less productive sections contribute less, reducing internal competition. Roots and attachment points also reflect this stability. Aerial roots anchor reliably where contact has been consistent. Hydration remains steady under normal conditions, and brief fluctuations are absorbed without immediate stress. This reliability supports flowering without the need for constant adjustment. Seasonal timing settles into a predictable rhythm. Growth strengthens when humidity and temperature align. Flowering appears within expected windows. Pod development proceeds without interruption when conditions remain within range. Recovery follows harvest with little urgency, allowing reserves to rebuild fully. Productivity at this stage relies on balance rather than output. Mature vines do not attempt to maximize flowering or pod count. They produce what they can support over many months without exhausting internal reserves. This restraint preserves long-term function. Environmental conditions continue to influence outcomes. Warm, stable periods support smooth development. Disruption still carries risk, but mature vines recover more readily because internal coordination is already aligned with their surroundings. Human management remains important, but its role shifts. Instead of encouraging growth, care focuses on preservation. Supports are maintained. Pruning is minimal and precise. Water and shade are adjusted gently rather than changed abruptly. As vines age further, growth slows naturally. Leaves remain functional, but extension is limited. Flowering continues, but yield stabilizes rather than increases. This change reflects efficiency rather than decline. The plant invests in maintaining what exists rather than expanding further. The surrounding environment adjusts in response to this steadiness. Pollination schedules align more closely with flowering. Disease pressure remains manageable when airflow and spacing are preserved. The entire system becomes quieter. Across years, the vanilla orchid becomes reliable rather than reactive. Growth resumes without urgency. Recovery completes without delay. The plant's needs are understood, and its responses are anticipated. This reliability does not eliminate risk. Severe storms, disease outbreaks, or prolonged drought can still interrupt production. However, vines that have settled into supportive conditions recover more fully because their internal systems remain intact. Over time, the orchid's life cycle reveals a consistent pattern. Growth builds capacity, flowering tests readiness, pod development extends commitment, recovery restores balance. Each phase reinforces the next. This pattern explains why vanilla cannot be rushed. Attempts to force production disrupt alignment. Productivity emerges when the plant's pace is respected rather than challenged. The vanilla orchid does not seek abundance, it seeks completion. Each pod represents a full cycle carried through without interruption, from flowering to curing. As the season draws toward its end, visible change slows. Leaves continue working long enough to return energy to the vine. Pod development concludes. Growth becomes quieter. In the final weeks, the vine prepares for rest without fully stopping. Energy remains stored. Attachment points hold. Internal flow slows, but does not cease. This transition is not an ending. It is a pause shaped by readiness rather than exhaustion. As conditions shift again, the same pathways will reopen. Leaves will resume growth. Flowers will appear when the vine is ready. Pods will form only if the full cycle can be supported. The vanilla orchid continues not by resisting time, but by working within it. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time learning about the vanilla orchid.